Hello, my name is David Faure and I work for KDAB. This video is about signals and slots in the context of multithreading. If you want to learn about the basics of signals and slots first, I suggest you watch another video from my colleague Jasper. Find the link under this video. If you found this video from a search engine when looking about different problems with signals and slots in multithreading, you should know that this is actually part of a series called Multithreading with Qt, in which you can find other earlier videos where you can learn about what is Qthread, how to start threads, how to finish them properly, and so on, how to re-implement run, and you should know about this before watching this video. There is also another video in this series which is about Qthread with event loops, where you learn about exec method and also about sending events to objects that live in different threads. You should know all of this before you can watch this one, otherwise it won't make much sense. So how can I communicate with a QObject that lives in a different thread? Qt has a convenient solution for this, which is called cross-thread signals and slots. We can use the usual signal and slots mechanism, but across threads, and that is quite convenient because we know this mechanism quite well, but you have to learn the various small things that work differently in the context of multithreading. Right, so I want to emit a signal in one thread, and then I want a slot to be called in an object in a different thread. And that other thread is the one where the receiver object lives in. That is the definition of an object living in a thread. That means this is the thread where the slot will be called. The mechanism that Qt offers us for this is called queued connections. Instead of the slot being called right away, as it usually is in the same thread, what will happen here is that the signal emission will be transformed into an event. The event will be posted to the thread of the receiver object, and later on, the receiver object will receive the event, process it, and that means the slot will be called. So there is a kind of a delay between the emission of the signal and the receiver calling the slot. That's why this is called queued, because it actually goes into a queue of events before being processed. The event itself is called a metacall event. This is internal to Qt, and it will be posted into the event queue of the receiver thread. For this to work, you have to make sure that the receiver object actually lives in a thread that has an event loop. If your receiver thread is simply a reimplementation of run and you have code in run, but you never go to the event loop, at no point will this thread be able to actually receive the event and process it and call the slot. So this is very important because both kinds of threads can exist with or without an event loop. You have to make sure that if you want to call slots in an object in the secondary thread, that thread has to have an event loop, which means either you don't re-implement run and it calls exec, or you call exec yourself, or you create a queue event loop. All of these things allow you to actually have an event loop to receive those events. Also, the arguments will basically be copied into the event, which means there needs to be a way for Qt to do that. And for some of your custom types, you will have to call QRegisterMetaType to make sure that the serialization of these arguments is possible. You can force a connection to be queued by passing queued connection as the fifth argument of the connect method. You don't actually need to do that in the context of multithreading because Qt will detect when the thread that emits the signal is not the same as the thread associated with the receiver. But it's good to know in general, if you want to use this delay mechanism inside of a single thread, you can use the queued connection argument to force it to be queued. So let's have a look at a few examples to put this into practice. In this first example, we have a secondary thread that derives from Qthread, reimplements the run method, and creates a consumer. In the main thread, we create a producer and we pass it along to the secondary thread so that it can connect the producer to the consumer with a simple connect statement. And then, as you can see, we call exec in the secondary thread to actually go to the event loop. So what happens here in chronological order is that the main thread creates the secondary thread. That's the first step. We pass the producer along. Then we call start on the secondary thread. And at some point, the run method will execute and it will do the connect. So the problem with this approach is that we might miss the few units of the producer initially emitted because we might not have connected first by the time the first units are created. So because if you think about this, when we call start on a thread, we have no guarantees of when exactly run is going to be called. It might take a while depending on the operating system and how busy the system is. So that's the problem with this approach. If the producer starts producing right away, we might miss a few items. So to really understand what's happening in general with cross-thread signals and slots, we can think of it this way. We emit the signal, it becomes an event. The event is posted into the queue of events of the receiving thread, in this case, secondary thread. And then later on, we get to that queue of events, process it, and that's when the slot is called. Okay? Let's see a better example for this problem here. How about we create both the producer and the consumer in the main thread. We connect them together. So at this point, we know that it's all set up. If a unit is produced, it will be sent to the consumer. Then we create a secondary thread and we move the consumer to that secondary thread using the move to thread method. Then we can start the thread, and when the thread starts, it will be able to process these events, which are basically calls to the slots that have been queued while the thread was starting up. So we are not missing the first few units here, assuming that they are emitted when the main thread goes to the event loop, right? We create everything, we set it up, we do the connection, we create the secondary thread. Only then we go to the event loop, and that's where the producer starts producing. So we don't have the problem of missing those because at that point, the connect is in place and everything works. We can also do this. This is just another example of queued connections. In this example, we have a secondary thread that emits signals regularly, or in this example, just once. And what we want to do is to connect that signal to a slot in the main thread. So we create the secondary thread, connect to its signal, and then when we start the thread, later on, it will emit the signal and we are ready, we have connected, so we can react to that signal. You can see in this example that we are using, or some might say abusing, the fact that QThread is a Q object. So we use it to create a thread, but we also use it to connect to its signals. So it basically plays both roles, the role of a thread and the role of a Q object. One thing to notice here is that the secondary thread does not actually need an event loop for this to work. As you can see, we don't even go into exec. We just do our work if we had any work to do, and then at some point we emit a signal. This is fine. We don't need an event loop on the side of the emitter. We only need one for receiving those events. Right? So it is okay to add signals to a QThread. We know that because QThread itself has a few signals, the started, finished signals. So we can add our own. This is fine. The connection will be queued because the rule for that is, let's compare the thread that is emitting the signal with the one associated with the receiver. In this example, the secondary thread is the one emitting the signal, and the receiver is some object that lives in the main thread, so the signal will be queued. This is fine. This is what we need. And what this means here is that the slot that is called some slot will be executed in the main thread. And finally, let me show you another example where we have a secondary thread, which derives from QThread, and we re-implement run to create a socket and we connect to that socket. What we'll do here is we are connecting that socket to this, which is the QThread subclass, which means we have slots in that QThread subclass. So basically, the instance of secondary thread is both a thread and an object. As a thread, it encapsulates the thread of execution where the socket runs. As an object, however, if you think about the rule, it was created by the main thread, so it has affinity with the main thread, which means its event processing happens in the main thread, which means its slots are going to be called there. And that is a problem here. This is not at all what we expected. If you read this code, you might think, okay, this is a secondary thread, it has slots, they are going to be called in the secondary thread. But that's not what happens here. Instead, this slot is going to be called in the main thread, and that might be a big problem for you. This is not at all what you expected. So basically, we end up with, yes, it is a Qt connection, but this is not at all what we want. It's going to call a slot in the main thread, and that is not what we expected. So what you can take away as a big rule out of this is to never define slots in a QThread subclass. If you need slots, you would define them in a separate object, maybe a worker object, for instance, and then you can move that worker object in the secondary thread or simply create it in the secondary thread so that they are associated, but never ever put slots in a QThread subclass. That is it for this video. In the next video, we will talk about the comparison between the multi-threading classes in Qt and the ones that are in the STL, in the standard library, so that you can pick and choose what works best for you between the two. Thank you for watching.